we can start now. The last time we were looking at a step-down chopper which had a switch here, and then we had only a resistive rod at the output. So this time we're replacing we are actually adding to the resistor another device, which is basically the inductor, and we'll be able to see on how it operates. So basically, when you are having a circuit from the input here with we're able to see that there is a device which you can connect here, a power device, to be switched on and to be switched off, on and off, as it supplies voltage to the output. Then there is a voltage source which is also indicated here and is given by E. What will happen? There are two modes of operation of this device. There is the point where you put on the switch, and the moment you put on that switch, what will be happening is that the current, we are going to have the inductor here storing energy. And at that moment, when the inductor is storing energy, of course, it will be increasing from the supply voltage. Then the moment you put off this device, that current which is already, or the power, the energy that is already stored in the inductor will be released, and it will be going around this output circuit, of course, where we have a diode which will be allowing that to happen. The moment we're having the first mode, please note that our diode is not going to exist in mode 1 because there's no conduction here to be reverse biased. We only have our current flowing through the inductor down the resistor and then to the input. Of course, when you're going to consider your voltages, you'll be able to subtract E from Vs because of the direction it has. Of course, this one is positive here, this one is negative when you're supplying from the input. So if you look at the diagrams that we have here, this is for mode 1. In fact, we don't need to indicate the diode here. We just need to have our current flowing through the inductor down and then to the negative of the power supply, which means that inductor will be storing energy. It's actually increasing in terms of energy. And then the moment you put off your switch or your power device at the input, what will happen is that that current or the energy which is stored in the inductor will be released through the resistor, and it gets around, of course, the circuit, because that circuit is the one which will be active. The other part is already disconnected, and we have that as a step-down chopper with a resistor and an inductor at the output. So you can see here our current increasing from a point of I1 up to maximum. We will call this I2, and then it falls down up to another current here, I3. Please note that this current and steady state, the current I1 and I3 will be the same. We'll actually equate them. But when we have a situation where the frequency is very low and this is discontinuous, then I1 will be 0. So you can start from 0 goes up, then it comes down to 0. But for a case where your frequency is a bit high, you actually have your current I1 starting from some value which is not necessarily 0, and then I3 the same. I2 will make the peak value, in which case you're going to have your I2 minus I1 giving us the I peak current or the peak current. So we can be able to look at those representations here, what I was trying to explain. And As you can be able to see, it has a chopping device, which will basically be our transistor. You can have it as a thyristor. Those power devices which you've used, or you can have it as a triac, which you can actually be able to put on and off. Then there is a resistor. We have an inductor at the output, and there is a diode which is connected in parallel to the inductor and the resistor, as you have been able to see there. And we have that voltage source, which is given by E. Sometimes you could have it at 0. It can also be having a value. That inductor, as we indicated, stores energy, which will be released to the resistor at some point when the switch is put off. And then that diode is called a freewheeling diode, which will be allowing now current to be flowing through in that circuit after the input switch has been put off. And those modes which I've discussed about, they are basically given here. So our mode 1, we also have our mode 2. And I've actually been able to explain mode 1 being the on state of our chopping device. Actually, the voltage will be such that you just have it off, on, but our current will be able to vary according to the waveform which I had shown you from the duration of from 0 to T1. Where of course our diode is reverse biased and our current is only flowing through the inductor and also the resistor, in which case our inductor is storing energy. So mode 2, we've said in this case the chopper is switched off. That is our device switching on and off. And we've actually indicated that the current will be going around within that circuit where we have the inductor, the resistor, the voltage source, and also the diodes. So there's some analysis which is done under mode 1. As we had indicated, you realize that your supply voltage will be given by the voltage across the inductor, the voltage across the resistor, and the source voltage you're having at the output. So in this case, you just need to be aware that our voltage in the inductor, I think from your circuit and network theory, you discussed about it and you know how you represent it. Then the one across the resistor, this is a very common formula based on Ohm's law. And with initial conditions, when we're talking about T is equals to 0, actually our I1, the small current will be given by I1, the DC value, because of that point where it starts switching on. Right. So we are talking about this point here. And then please note that when you solve this equation and make I1 the subject of the formula, I mean, I just make I, not I1, but make I the subject of the formula, you need to be able to get your current, your instantaneous current, we call it instantaneous current, which will be the current from I1 all the way to I2, will actually be given by I1 e to the power of negative t, R divided by R plus Vs minus E divided by R, then 1 minus E to the power of negative t over t negative tr over R. Remember, in the inductor, this is how you present your current. With the capacitor, you are aware of that formula of the e to the power of negative. It's usually negative RC divided by T. I think that's what you usually have for the capacitor. but for the inductor, it's represented this way from your CNT. And please, this will take place from 0 to T1, in which case, remember, we're talking about our K, which will be the duty cycle at that point where the input switching device is actually on. So at the end of T1, that is when you move from T is equals to 0 all the way to T1, we are talking about your 0 to T1 here. So it is actually what's represented from this point to this point. And then at this point, here is your I2 maximum. It will be given that way. And after that, of course, now your current will be flowing through the output device, I mean the output component. So from mode 1 is this one, where this diode is not necessarily your voltage will be from this point to that point on, and from T2 onwards to the end, your chopper is off. No voltage is applied from the input. And in that case, your current will be reducing from I2 to maximum. To be said that this can actually be which conditions you've taken. So based on that, we can be able to get the equation for second mode, in which case you are going to have the voltage across the inductor, the voltage across the resistor, and the source voltage will be equal to 0, because this time we are not supplying a voltage from the input. And from Ohm's law, of course, you're going to have your current being given by your voltage being given by I times R. But based on the inductor voltage, it will be R, of course, change of I with respect to T, and that we are considering I2, because R, the voltage across R, and the E source voltage, which currently I1 on. But when it's off, we say the voltage now will start, our current will start moving around through the diode, then it goes to the inductor, the resistor, the source, like that, until the other point when again we switch on this chopping device, which is at the input. So based on those two diagrams, you can be able to get our voltage and the current. We just taking ideal cases, so we don't need to consider the voltage across the diodes for ideal cases. But otherwise, if you consider it, it will be depend on the type of diode that you are dealing with. So it can also be included. But for now, let's not include it, because you're dealing with, most of the time we're dealing with high, slightly high voltages, where we take that one of the diode to be a bit negligible, or to be negligible anyway. So that's why we are not putting it here. And of course, from this equation, and using, you guys, I think you've known that you can also use Laplace transforms to be able to generate that equation the way it's appearing here. And that will be giving us our current I2, which will be varying from the maximum peak value to the minimum, which is given by your I1, or which you can say is equivalent to I3. So as you move on from T2 all the way to, or I mean from T1 all the way to T2, that is the middle point. If your duty cycle is 50%, or 0.5 for K, then you're going to have your current reducing from a maximum of I2 all the way to a minimum of I3. But as we'll be able to note, under steady state conditions, this current will be equivalent to I1. So I3 will be equivalent to I1. And that's what is indicated here, that under steady state conditions, I1 is equal to I3. And then you can be able to determine your peak current, the I2, and also the I1 can actually be obtained using those equations that we've had up there. In which case, now you introduced your duty cycle here. You have actually removed the T1, which was included, and also the T2, which is included in those equations. So this first equation will be given by I2, and the second one will be given by I1. Which is actually equivalent to I3 as we have noted. These particular points. So we are talking about this I1, this I3, which in the steady state conditions will be the same. And then we are also looking at I2, the peak value that you can be able to get. So those equations that we have here are giving us those two currents. And of course, if you want to get the repo value, you just take I2 minus I1. At some point, we are going to see on how it actually comes to Vs divided by 4FR when we are considering the T here and frequency, the relation, that is a period you are using, and K is our duty cycle. Of course, when you're talking about the average, or usually it's the average current actually, which is given by I2 minus I1 divided by 2. But I want us to look at this representation here. This one, the change of I is equals to I2 minus I1. And if you use the two equations that we had there, they will actually be able to come to this representation. The equation for I2 and the equation for I1, these two equations, these two, if you subtract and take the values that you have in here, all these parameters which are indicated in relation to those two currents for I2 and I1, of course, the equation comes to this, though it's the same one that we're having at this particular point. That is 717 for the book. So for maximum repo, I think you take the rate of change of that variation of current, delta I, with respect to K. So you differentiate and equate to 0. And if you do that, then I think from mathematical analysis, which I cannot be able to go into the details at the moment, will actually result to Vs over R. Then there is a term here, R divided by 4FL. And these values usually, when you're talking about 4 times frequency times the inductance value, if it's much greater than R, and based on this equation, then that's a tan theta becomes theta, and I think that's why we are eliminating this part from that equation. And if we put them together, then your R will cancel with R. We are left with Vs over 4FR as the change of your current. And I think that will be what we have in here. I believe they are basing it on this representation. I think I have to check what happens. This is not tan, it's actually tan theta. Equivalent to theta. And of course, from your mathematical analysis, trigonometrical ratios, I think this would be equivalent to EX minus E to the power of negative X, EX plus E to the power of negative X. And that's why we are taking now the values for our resistance, frequency, and F. And based on this equation that we have up here, which will then result to the final equation given by change of I max, which will be Vs over 4 times frequency times the inductance value. So then the root mean square value, you're going to take the I squared, that's I1 squared. In fact, we are looking at a situation where we have our I squared. Okay, you square the value, then after you square that value, you integrate, and after integrating, you get the average. After you get the average, you divide by, actually you get the square root, not you divide by, but you get the square root. That's the root mean square value, which is given from this equation here. So your root mean square value can be found from, you take the I squared, then from the I squared, you integrate from 0 to your kt, that is T1, with respect to T, and then you do the average, of course, divide by kt, and after that, you do the square root, which then will give you now the values of I1 and I2 in this relation, in this form. So there's an example which is done here, and it's indicating there's a chopper which is feeding an RL load that has as indicated, of course, in the diagram that we had for the chopping device, plus the resistor, the inductor, and then your supply voltage is 220 volts. You realize now that voltage is high compared to the one for the inductor, because most of the time these chopping devices will be used to deal with the high power, the 220 volts or 240 volts, which we have as our supply currently in Kenya. Then we have a resistor of 5 ohms. Of course, those resistors are the ones which you're dealing with high power, and you don't want to lose so much power around here, so you make the resistance a bit low, around 5 ohms. And you need to note that this resistor, the size will be not that small, it's actually large, so that you can be able to dissipate the heat energy generated. Because here we are dealing with high power. You look at the power supply. Then the inductor is 7.5 millihenries, and it's operating at a frequency of 1 kilohertz. It means you're looking at the period from 0 to t is actually 1 over 1000, which will be given by 0.001 as a period, but that's the frequency you're operating in. And be able to get also our K will be given somewhere, E is 0. So calculate the minimum instantaneous load current, which is given by I1, peak instantaneous load current, which is given by I2, maximum peak to peak load repo current, which will be given by that value where you're subtracting I1 and I2, and then the average value of our output current, which is IA, and then the RMS value. And we saw IA is just taking I2 minus I1 divided by 2. And I naught is the root mean square value. Then they're also indicating that you calculate the effective resistance. I think this were done somewhere in one of the analysis earlier. And then the root mean square chopper current, IR. So let's go through that analysis, and we put the values down. Vs is 220 volts, R is 5 ohms, L is 7.5 millihenries, E is equals to 0 this time, K is 0.5, F is 1000 hertz, and the equations that we had up there, we can actually be able to substitute the values accordingly. And I want you to check whether that is what you are getting. We substitute the values. E to the power of K is 0.5. You take your T is 0.001. Then you take your resistance, you know it's 5 ohms, divided by R, which is, we had it at the millihenries. What was the actual value? So 7.5 millihenries. And E is 0. Vs is 220. Divided by your R, the resistance, which is 5 ohms. Then you also substitute up here the actual values for KT, R, or R. And then you determine. Please let's do that from your side using your calculators. Let's try to get this I2 in terms of I1. Let's substitute the values.
Safaricom. For help on customer queries, please.
So let's take those values, 0.5. We multiply by 0.001. We multiply by 5 divided by 7.5. Exponent 3 negative, and then we get the natural log of that inverse. It's 1.3, that's 1.4 I1. So there's a value, you determined, you checked. Who has calculated? Point 5 times 0.001 times 5 divided by 7.5 exponent -3, and then you negate that value to determine that. Yeah, so you guys, you cannot even help from your side. So please know that we didn't put a negative the first time. So 0.716, that's what you are getting. For this value, 0.176. So we have confirmed that using that formula, we are getting that. And of course, if you use the same for the next value, to plus 12.437, and for I1, you also get 0.7165. After all, they using the same parameters. I2, but your E is 0. So in that case, you're getting the equations being simultaneous equations, and you can substitute. So you take your I1, substitute it here, 0.7165 I2, and from there you determine your I2. And you need to confirm that it basically comes to 25.63 amperes. And I1, 18.37 amperes. Maybe you can just confirm that. And then, of course, based on those two values, I1 and I2, you get the difference. That will give you the change in I, 7.26. I think I'm not talking droughts. Please check your internet also, because from my side, I believe it's okay. And then the change of my Imax, I remember the formula that we were using there. That formula for changing Imax, which is Vs divided by 4 times the frequency 1000 divided by air, I mean multiplied by air, 7.5 times 10 to the power of -3. And that results 7.33 amperes. Please need to confirm those values. Members can also confirm whether I'm breaking. And then the average current, we said it's supposed to be, you take the 2 and divide by 2. So take the 2 current, then you divide by 2, the sum, and we already have 25.63 for I2 and 18.37 as I1. Dividing by 2, you get 22. That's after you get the sum. So based on the formula that we had earlier, the average source current will be given by IS, which will be K times IA. I think this one we have done much earlier, and that will give us 0.5 times 22, which will be 11 amperes. So the input resistance also, we did the first time when we were handling our step down chopper. We have RI, we had RI is equal to VS or IS, which you take to 20 divided by 11, that will give you 20 ohms. And then finally, when you're looking at the RMS value, you'll be able to take the square root of K, I naught, and I naught is given by the equation here, where you need to take your values of I1, I2. You indicate the means idea, substitute. Then after you do your analysis, you get the square root, which will then come to 15.63 amperes. So we've taken that example so that you can be able to understand those values. And the formula which I indicated in that first example of a step down chopper with a resistor and an inductor at the output. And please know that the inductors and resistance representation will be what kind of device can you have at the output there? It will actually be a motor, because motors have got windings, which will give us the inductance and a resistance, of course, through the wire. So we can rejoin, continue with the next case.